Yeah, so now normally we know that we have all studied and we have worked with conventional generators, mostly synchronous machines, which are normally hydro, coal, thermal, gas, so diesel. So most of them are conventional generators, which are mostly synchronous machines. But with this non-conventional generation, what we normally mean is inverter-based or asynchronous generators. And most of the renewable generators, solar farms, wind farms, and other batteries, for example, are mostly inverter-based generators. Go to the next page. So why we are talking about this renewable generation is there is a massive change in the participation or the portion of generation in most of the power systems these days. For example, in Australia, we have a significant uptake of renewable generation, and conventional generation is reducing, or they are retiring most of the coal-fired generators or gas turbines. They are retiring with time in coming years. So there is a transformation happening. Then, oh, sorry, I'll go back. So I'll briefly discuss about in this presentation how this composition of generation is changing, especially in Australia. Sorry about this, but I am using most of the examples from the Australian national electricity market because that's what I am used to. I have not looked at what's going on in Sri Lanka at the moment in the present power system. And then main issue that we have is renewable generators or this asynchronous generation is different to synchronous machines. So we will talk a little bit about the differences, what asynchronous generation is, and then why they are different to synchronous machines, and the challenges associated with them, especially when we have higher percentage of renewable generation. Because if you have only 1 or 2 solar farms, wind farms, or only 5%, 10% of the total generation capacity, it's not the massive issue. But when you have 50% or even more than that percentage of renewable generators in the system, there are major issues associated with the power system planning and operation. So we'll discuss about the issues, and also briefly, I will discuss about the likely solutions that we are considering. So if I look at the energy transformation, we know that traditional power system is dominated by synchronous generators, mainly coal, hydro, in some countries nuclear and gas. For example, in Sri Lanka, we have coal and then gas mostly and diesel. In Australia, very much similar. We have hydro as well in Sri Lanka. They are mostly synchronous machines. Then when we look at the solar farms and wind farms with time, especially in the last 10 years, there is a very high uptake of solar and wind farms. And if you look at this plot below, this is the forecast of generation in Australia national electricity market. We can see there is a massive increase of the solar generation, distributed PV. They are mostly residential solar and also commercial solar. Then utility scale solar, that means, let me just change my pointer if I can. Utility scale solar, that is more solar farms or wind farms, solar farms, then wind also mostly wind farms. So you can see significant amount of generation capacities taken over by solar and wind in coming years. If we start from this year, even now, if you look at Australia, even now there is a significant uptake of solar and wind, about 50 gigawatts of capacity or even more. But if you look at coal, which is the black coal, the black bars, and also the brown coal, you can see they are gradually reducing. So what we expect is that there will be a significant reduction of coal generation in the next decade. By 2032, 33, there will be hardly any coal in Australian power system. Then gas and hydro very much remain the same. Storage, you can see gradually increasing this. And distribution energy storage, again, this is more energy storage batteries, but mostly in distribution networks, residential batteries, which are more coordinated. That means there can be batteries linked to a network. That network operator can control the battery, whether they are charging or discharging, depending on the system conditions. So what we can see is there's a significant reduction of coal power generation. If you start from, can you see my pointer? It's very small. Let me just go back to the arrow again. So you can see if you start from 2023, 24, there is a significant reduction of synchronous machines, but uptake of asynchronous generation. So what are the issues? Because if the solar farms, wind farms are similar to synchronous generators, we will not have any issue. They will be just replacing the source of energy. But there are significant differences. If you look at the asynchronous generation, we know that they are not dispatchable. That means they are intermittent. When sun is there, they can generate solar farms, or when wind blows, wind farms can generate. So there is a significant risk with supply reliability. That means if you only have solar farms or wind farms in the system, you have a significant risk with supplying the demand. And also there can be times where you have excess generation, which is fine. You can just spill the excess energy, but there is no real risk to the network. But there is a wastage of energy if you do that. Then another technical issue is inertia contribution, because we know that synchronous machines contribute inertia to the power system, which kind of resists the frequency changes. Higher the inertia, synchronous machines, because they have a rotating system, they can control the frequency, or they help the frequency to remain at 50 Hertz. If there is a disturbance in the system, the inertia in the synchronous machines resist that the frequency change due to the disturbance. But these asynchronous machines normally don't produce any inertia, or no, so they don't contribute to frequency control immediately if there is a change. They can be still used for frequency control following a frequency change, but they don't contribute to inertia. It's same with the fault current contribution. Synchronous machines, we know normally during a fault, there is about 4 or 5 times its rate in fault current contribution or fault level contribution. For example, if you have a 100 MVA synchronous machine, normally if there is a fault nearby, we can expect it to contribute about 400, 500 MVA fault level. But asynchronous machines are different. They are normally inverter based. At most, they can produce a fault current similar to the inverter capacity. If it's 100 megawatt or 100 MVA solar farm or a wind farm, they can contribute about 100 MVA fault level. So what are the issues? If the fault level contribution in the system or fault levels are reducing, we know that most of our protection systems, to clear faults in the system, we rely on the fault currents. So if the fault currents are reducing, protection systems will have problems in identifying faults or detecting faults. So that could be an issue. And also voltage control. We know if the fault level is high, if there is a fault, normally the fault voltage change is less. We'll talk a little bit more in detail later on. So voltage control will become an issue as well if there are fault level reductions in the power system. And another main issue is these most of the present day inverters we call them as grid following inverters. That means they rely on the power system or the existing system voltage waveforms for their correct operation. They follow the grid voltage. We call them as grid following inverters. So if the system strength is low in a particular area, sometimes these grid following inverters will struggle to maintain stable operation if there is a disturbance. And there can be control issues as well. And another issue is the resource location, because most of the established grid are near the load centers. For example, it's same in Sri Lanka, say near Colombo or near major towns, you have most of the major grid. But sometimes solar farms, wind farms, the resource could be strong in some further away from the network. So high resource areas could be not near the existing grid. So that's another issue that we have when it comes to solar farms and wind farms. So that's a very weak networks have to carry the generated power from the solar farms and wind farms. So they are the main issues that we come across when we consider renewable generators or asynchronous generators. For example, I have few examples. Now, this is just trying to show the impact of intermittency of the generation, or um, uh, the impact on supply adequacy or supply reliability. This is a snapshot of the Australian Eastern power system, that is the national electricity market, uh, from a software application. Now, what you can see is the topmost end, you have the Queensland state, then we have New South Wales, Victoria, South Australia, and Tasmania. So they are all interconnected through transmission lines, all 5 states. And on this particular day, what we could see is we have about now 10, 15 gigawatts of wind generation and about similar amount of solar generation in the whole electricity market. But on this particular day, there was very low solar. Now in this plot, you can see, I'm not sure whether you can see them because this diagram show that, for example, if you look at the New South Wales, at that particular time, the price per megawatt hour, $602 per megawatt hour, the price. Then it shows the market demand about 10.3 gigawatts or 10,298 megawatts. It shows the generation available in New South Wales and also the inertia in New South Wales of the inertia contributes 44,000 about megawatt seconds. Then also it shows the generation kind of split. There is about 5,700 of coal, 566 megawatts of hydro, gas, then no hydro at the time. So all the hydropower stations were not running at the time. Then you can see 53 megawatts of wind and 465 megawatts of solar. So what we could see is in New South Wales at that time on 29th of January, there was only 53 megawatts of solar out of about 3-4 gigawatts of wind out of about 3-4 gigawatts of wind generation. It's same in Queensland, only 59 megawatts. It's same in Victoria, only 192 megawatts. So what we noted on this day is there was significant drop in wind across the whole country. So that caused issues with the supply of the load. So we experienced this lack of reserve conditions. So in New South Wales, we experienced there were low reserve conditions, or we call this as lack of reserve condition 1, 2, and 3. Normally what we say is lack of reserve condition 1 means there is not enough reserve to cover two largest generating units, because normally we like to, if there is a generator trip, we would like to allow the trip of the next generator, because a generator can trip at any time due to a fault within the generator, say a coal power generator or hydropower generator. Normally it's about 700 megawatt units we have here, coal power units. So if one unit trips, LOR 1 condition means you can't cater for the next generator unit. LOR 2 means you can't cater for the first unit trip. LOR 3 means you are already short of supply. So on this day, the demand wasn't that high because our peak demand can go up to about 15 gigawatts. It's only 10.2 gigawatts. Still, we saw LOR 1 conditions because there wasn't enough solar and wind at that time. And if you look at this one, this is another day where we had high solar, say 2,000 megawatts of solar in that day. And if you look at this one, there was high wind, about 1.1 gigawatts of wind. So it's very intermittent. The solar and wind generation can change with time. We have forecasting systems. Solar normally generally easy to forecast because normally if it is a sunny day, you get high solar generation. But if it is with wind, it's difficult. but there are forecasting systems, so you can forecast what wind you can get in the coming 5 days or 5 to 6 days. But still, you can't control. You will have wind or you will not have wind. So it's very difficult to rely on them in the longer term. So you have to, if you are talking about high solar or high wind penetrated systems, you have to have other means to ensure supply reliability. You can't just rely on solar and wind. You have to have dispatchable generation in case there is not enough solar and wind. So what we are doing is there are lots of measures being taken over here because we know that diversity of renewables can help. Now on that particular day that we discussed, it wasn't the case because there wasn't much wind across the whole network, but generally you will see that there will be some wind in somewhere. It could be Queensland, it could be Victoria. There will be reasonable amount of wind. Solar again, similar. There could be a sunny day in Queensland compared to New South Wales. So you can rely on the diversity of renewables but then you need lots of transmission to rely on that. So there is lots of work happening. If you look at this diagram on the right, you can see all these lines, transmission lines shown. They are the new transmission connections being planned in the next 10 years or so. There are a number of interconnections. New South Wales and South Australia, new interconnector is built, this gray line. You can see it's expected to be commissioned in 2024. Then there is another interconnector, not interconnector, transmission connection from this southern region to northern region of New South Wales, which is called 500 kV double circuit line. And similarly, Victoria, New South Wales new interconnector, this green one from Victorian side to New. So there are lots of interconnectors being planned. The intention is we can rely on this high renewable generation in somewhere to supply the load in somewhere else if there isn't enough generation in that region. Then also, it may not be enough. You have to have lots of storage because if you don't have coal generation because they are retiring, you might not have gas generation at the time. So generally, you would have to rely on lots of batteries. Say, for example, there is a battery that's planned 850 megawatt battery near Sydney. So we are working on lots of batteries, battery storage systems, because then if you have enough batteries to supply the peak demand, you should be okay. You can, during the daytime, when there is lots of solar, you can charge the batteries. During the evening, you can use them to supply the demand when the solar drops. And also pump hydro is another one. There is a large pump hydro station being built at the moment, about 2 gigawatt pump hydro station near this southern region of New South Wales. Then you still have to rely on hydro and gas, especially gas turbines, which can start in within 5 to 10 minutes. So you have to have gas turbines in these systems to meet the peak demand. In addition, we are looking at demand management measures as well, because there can be loads that can drop if we are short of supply, especially aluminium smelters or large loads. There are contracts. We are looking at having contracts with some large generators, large loads, large customers, so that they can reduce their generation, or they can go to an internal gas turbines or a diesel turbine, diesel generator, and reduce the grid demand. So there are lots of things taken into account, because if not, you will have serious problems supplying the demand. Then in addition, there are, not sure whether you have heard about these renewable energy zones. There are lots of work happening to develop renewable energy zones. That means you identify a large area, for example, in this diagram, the Central Orana renewable energy zone. That's a large area, about 200 square kilometer area. You plan solar generators, wind generators, and storage systems, and you build transmission from that area to the main grid. So that's been happening as well. There are a number of renewable energy zones. Mainly, they are government initiatives. These are New South Wales government initiatives. There are 3 gigawatt solar generation or new renewable energy zone. Then there is another 8 gigawatt one happening there in this New England area. So there are a number of renewable energy zones that are being developed. So the intention is you develop zones where you have transmission built from that zone to the main grid, and you ensure that that zone is capable of generating consistently. That means not only solar and wind, you will have storage as well in that area, so that if there is not enough solar, you rely on that storage to supply the demand. So that means if you want to transition to a high renewable network, you have to do lots of things. You can't just expect things will happen naturally, because what happens is when you have high renewables, normally you will start to see not enough profits for the synchronous machines, coal generators, gas generators. Then they will start to gradually take out their generation. That means we will start to see, we have already started seeing significant reduction in synchronous generation in Australian power system. It's happening everywhere, even in Sri Lanka. Sri Lanka situation is much better because you have lots of hydro compared to other countries. Uh, so you can still rely on hydro to supply demand, but then you need to have water for that. But in most of the other countries, you rely on coal mostly, and the coal power stations are now retiring because most of these power stations were built about 40, 50 years ago. So their kind of technical life is coming to an end. Then they find that there is no point of investing again to refurbish the generators or refurbish the coal stations or these boilers and like that, because they are not getting enough income from selling energy, because there is lots of solar and wind in the network most of the time. So you have to, if you want to go to a high renewable network, you have to do lots of things. It could be more transmission, it could be more storage, it could be all these renewable energy zones. So there will have to be lots of plans to do that. Then, so that's more about supply demand balance. So how we can manage transition of generation to a high renewable energy system where you can supply the demand. But then there are technical issues as well. Even if you have generation, there are a number of technical issues. As we mentioned earlier, inertia is one problem. If you look at this plot, show how the inertia changes with time, especially when we have different coal power plants retiring. Say this year, we are going to see this Liddell generator, which is a 2000 megawatt generator. They are retiring next week, or they are starting taking out their units next a couple of weeks. So they will completely take out their units by the end of April. So that's about 2000 megawatts taken away from the network. So that's not only megawatts, but also the inertia contribution from them. Then in 2025, another generator, about 2800 megawatt generator for 700 megawatt units, they are retiring in 3 years time in 2025. Then another generator will retire in 2029. So you'll see that the inertia contribution dramatically reduced with time. So you'll have only a couple of generators after about 33, that is in 10 years time. So we have to do something about this. So, and what are the issues? I think you are very familiar with this swing equation, where we know that rate of change of frequency, or DFO dt, is dependent on the inertia. Higher the inertia, rate of change of frequency when there is a disturbance is low. That is, inertia resists the frequency change. So this plot also here, it shows if you have reducing inertia, rate of change of frequency will increase, because the rate of change of frequency, or ROC-off, is 1 over inertia, if you look at here, proportional. So if your inertia is reducing, that means rate of change of frequency will start to increase when there is a disturbance. It could be a generator trip, it could be multiple generator trips, or interconnector trips supplying the demand, supplying megawatts to a certain area. So frequency control can be significantly affected. Then what's the issue? The main issue is, we know that if there is a significant sudden drop of frequency, the systems we have to control the frequency might not have enough time to respond. Say if we want to keep the frequency around 50 hertz, so we have generator governors help in that frequency control when the system generation and load changes. Then also there are if there is a significant interruption, we have under frequency load shedding or frequency generator tripping. But they need some time. They monitor the frequency change in the system and then respond. Even generator governors, we know that if there's a frequency change, then the governor may take action to increase its megawatt output by opening valves. So it's same with under frequency load shedding schemes. They monitor the system frequency. If the frequency drops below a certain level, then they take time, they analyze it, and then trip some load to help the situation to balance the generation and the load. But the reduction in inertia will increase the rate of change of frequency, and that will cause problems with these systems because the frequency drop could be too dramatic. You might not have time for these systems to operate. That happened, for example, in 2016. There was a blackout in South Australia. That's one of the states in the Australian system because there were significant storms in the area, and about 5-6 wind farms tripped at the same time. So it's about several hundred megawatts of generation suddenly tripping. That overloaded, and there is an interconnector from Victoria to South Australia. That trip of wind farms overloaded that interconnector and it tripped as well. And that megawatt generation deficit caused a significant frequency drop, and system under fixed load shedding system couldn't cope with that fast frequency drop, and then the whole system collapsed. So that's a very high risk that we see in the national electricity market of Australia at the moment, because with more and more renewable generation, we see more and more synchronous machines taken off, and that could lead to significant inertia reduction. Normally, a single generator trip, we are still okay. But if you have a multiple generator trip event due to a power station fault or something, you can sometimes have 4 or 5 generators tripping close to each other immediately after one another. And if something like that happens, we will struggle to manage frequency. So what are the solutions, possible solutions we can have to address this inertia reduction? One primary solution is use synchronous condensers. We use it significantly over here now these days, especially add flywheels to the synchronous condensers, because synchronous condensers can be used to control voltage or help with system strength as well to contribute to the fault currents. But normally, if you just have the generator or the machine only, you will not have a high inertia. So what we normally do is we add the flywheel to the shaft of the generator, which can add to the inertia of the system or the energy in that rotating system. So that's widely used. Now, for example, this new interconnector that we are building between New South Wales and South Australia, we noted the need for voltage control along the way. Rather than using static bar compensators or other static devices, we introduced synchronous condensers. And then also not only that, we introduce high inertia synchronous condensers. That is the inertia constants of about 7 seconds, which is fairly high. So that's one thing that's been considered and done across most of the power systems, not only in Australia, many other countries where there is high renewable penetration. We use synchronous condensers. Then not only that, now there is lots of research happening with inverter technology also. Now, I mentioned that most of the existing inverters are called grid following inverters, but that means they rely on the grid voltage. They can't form a grid, or they can't operate without connecting to an existing AC system. But there are inverters now which are called grid forming inverters. As the name implies, that means they can form a grid, or they can just run as a islanded system. And they are mostly kind of voltage source inverters. That is, they operate as a voltage source. Grid following ones are normally operating as current sources. So they follow the system voltage and introduce the current to get the required P and Q. But grid forming ones, they introduce a voltage and an angle. So they are similar to synchronous machines. So there are lots of grid forming inverters are being introduced these days, number of different manufacturers. So that's one way of addressing this inertia drop. Similar to I will discuss later about system strength, the same thing. And similarly, there are now other technologies. The second one, grid following inverters with synchronous machine mode. That is, it's still a grid following inverter or a current source component. You can see in the second diagram on the right, bottom right. But they have another component, a control component. They model a synchronous machine. So what happens is under normal operation, this synchronous machine or rotating component is not engaged. But whenever there is a disturbance, if there is a frequency change in the network, they monitor the rate of change of frequency, and then they introduce a current or power to counterbalance that rate of change of frequency. So they are called normally synchronous machine mode, or sometimes if you have heard about Tesla inverters, they have this virtual machine mode. So that's another one that are being introduced in the market these days. So there are grid forming inverters, which are more voltage source, and then also current source or the traditional inverters, but they introduce this virtual machine mode or the synchronous machine mode component. So there are lots of things happening. That means we might not have serious problems in the future, although there is a high penetration of renewables, because if they are using these grid forming inverters, they will be able to produce or help the system with the inertial contribution. This is just an example. We are now in Australia, normally transmission network service providers, say this Transgrid, which I am working in, is one of the network service provider for New South Wales. So we are responsible for providing the inertia to the system. So if there is a inertia shortfall, this Australian electricity market operator, they will declare a gap. They will say that on this date, there will be a certain gap. Then the transmission network service provider is responsible for filling that gap. So we are considering synchronous condensers is one form of introducing inertia to the system, but also we are looking at, can we use these batteries to contribute? So we have a trial project at the moment, just a 50 megawatt battery in a place called Volgrove, where we use this Tesla's, they are grid following inverters, but they are equipped with this virtual machine mode. So they can contribute to inertia. That means if there's a generator trip or generator stripping or load stripping, or there are faults that cause a megawatt difference in the system, they can help with frequency control or manage frequency control. And these are some measurements coming from that system at the moment. We are just monitoring it because this is a research project that we are doing to see how much we can rely on these grid following inverters converted to contribute inertia with this extra virtual machine mode, or even grid forming inverters. What we can see here is now, this is a real incident where we had a 260 megawatt generator tripping. You can see the blue curve is the megawatt output of that battery system, and the green curve is the frequency drop. You can see immediately at this at the point of the incident, since this is relying on the rate of change of frequency, it introduces a megawatt output. So this initial increase is due to the inertial contribution of the battery. Then when the frequency drops, it has another component, which is normal frequency control. So when the system frequency drops because of that generator tripping, sorry, we can see it contributed more megawatts. So this inertial contribution is the important bit. And in this right-hand plot is a similar one, but a simulated one. And we compare the grid following and grid forming modes. In this case, now this is a load trip, 300 megawatt load trip. You can see the green curve is the one with that virtual machine mode or the synchronous machine mode enabled. You can see immediately at the point of load tripping, it immediately reduces its megawatt output to help that frequency control. But if you didn't have that virtual machine mode, the other blue curve is without the virtual machine mode. You can see nothing happened immediately, but when the frequency dropped because of that load reduction, it responded. It still reduced its megawatt output, but its response is delayed because it relies on that measurements of the frequency, and frequency need to drop due to the incident, and then only it will respond. So the importance of this inertial contribution is it will respond immediately to resist that frequency change. If I move to the, so that's one issue that we have, inertial contribution of the synchronous machines. We are losing that when the synchronous machines are being taken off from the system. But there are means now people are looking at, lots of research happening with the inverters themselves, or synchronous condensers are widely used these days across networks. And most of the batteries now, we have got number of batteries preparing to connect. Most of them are grid forming batteries. That means they can contribute to this inertia contribution. Then another technical issue is system strength. That is the fault level contribution due to these synchronous or the asynchronous machines. And system strength, we know that it's normally related to the fault current within the system. And if you, or fault level, if the fault level is high, we know that normally near the generating stations, fault level is high, because if there is a fault, that generating station will contribute to the fault current. So normally we say that if the fault level is high, the system strength is also high, or the strong area. And so typically, if you have high number of synchronous machines around that area, you will have a higher system strength. But if you have number of lines, parallel lines, we know the impedance is low from the generating area to the load area, or the new network connection points. Then again, the system strength will be high, because if the impedance is low, that means higher the impedance from a generating station to the load areas, lower will be the system strength. I think it's fairly straightforward. And if you look at the New South Wales network, we can see there are remote locations. You can see these green areas, that marked areas. They are very weak system strength nodes. For example, from this substation called Bironga to this furthest away point, Broken Hill, it's about 260 kilometers. Then from Bironga to Darlington Point, this blue line, it's another 400 kilometers. So they are just a single line going to this area. Then we have wind farms, solar farms connecting in these areas. So what we can see is system strength, or the fault level, is very low in this area. But if you consider near the Sydney region, that is near this right-hand side, there are a number of synchronous machines. You can see these green squares are the coal power plants. Lots of coal power plants near the Sydney region. So they contribute to the fault current. So at the moment, we have a strong system strength point of view, very strong. But the problem is most of these generators will retire with time. In the next decade, almost all these generators will retire. So we will not have any synchronous machines or coal power plants near Sydney area as well. So we have already started looking at what we can do to make up that reduction. So we know this is fairly electric theory. If we have low fault currents, there can be protection issues. And also if there is fault level, or the fault level is low, when you switch out reactive plant, the voltage change can be high. It's same with the angle changes. If a generator trips, the system angle change will be high if the fault level is low. This is just comparing two bus bars, a 330 kV strong bus and a 220 kV very weak bus. You can see the short fault levels, 15,000 MVA at the strong bus. Weak bus, it's only 500. Then the fault currents, you can see if there's a fault, three-phase fault current is about 29 kA and 1.5 kA at the weak point. And these are the impacts. Voltage change, if you switch in 100 megawatt capacitor, at the strong point, only 0.7% voltage drop, voltage increase. But if you switch in a similar size capacitor at this weak node, you will have a 20% voltage drop. That means you can't have such a large capacitor at this location. So that's another thing. As you might have seen that normally when you move away from the strong or generating stations, size of the capacitors, we reduce them because we can't connect switch in a large capacitor to a very weak point. Normally, you have to reduce the size of the capacitors. It's same with the angle change. If you have a system disturbance, say a line tripping, you will see that at strong points, voltage angle change is minimal. But if you move away from the network, you can just do a load flow study and check this. You will just say open a line, you will see further away from the network, the angle change will be much larger. So that could cause problems for the connecting generators to maintain stable operation. And this is another example of issues with low system strength or low fault levels. You can see some interactions with different plant. This is the interaction with the solar farm and the SVC. What we noted is there is about 7 to 8 hertz oscillation happening in the network. Voltage oscillation, you can see it's about 7%, 8%. If you look at about 7.07 per unit, it's about 7 to 8% voltage oscillation, sustained oscillation occurring because of the low system strength conditions. So we have seen this across many areas, weak areas in New South Wales and across the Indo-Australian system, where because of the high penetration of renewables, low system strength areas, there can be interactions between different control systems, solar farms, wind farms, or if there are SVCs in the area, and you can see these voltage oscillations. And what are the measures? Normally, main measure at the moment to increase system strength is use synchronous condensers. This is an example. This plot shows an example where we did a study for a solar farm connection. You can see now the three graphs show the output of a SVC nearby in that connecting area. The gray curve is when that solar farm is out of service. You can see after disturbance, there is an oscillation, but it settles down. After about 5 seconds, it settles down, the gray one. But if you add the solar farm, what we see is this blue curve. You can see there is a sustained oscillation after the same disturbance. So this is not acceptable. We can't accept a connection, new generator connection, if we see something like that. So what we suggested to them is you need to fix a synchronous condenser to fix this system strength issue. So this is a simulation showing what happens if you add the 60 MVA sync on. You can see after the disturbance, it has a very nice stable waveform. So synchronous condensers are widely used to help system strength because they can add to fault current, and they are also fairly established synchronous machines. We use them to help with inertia as well, but mainly widely used for system strength. Then now these days we are investigating grid forming inverters also, batteries, to address these issues, say similar issues, say if there are oscillations, rather than a synchronous condenser, we are looking at adding a grid forming inverter or battery to do the same thing. And we have seen that there are positive outcomes. So this is the last slide. So to summarize, what's the time here? Of course, 40 minutes. Yeah, so high penetration of asynchronous renewable generation is happening. We can't stop it because there are lots of incentives from the governments or public to go for this environmental friendly generation forms. And then they are very cheap as well. If you look at the synchronous, say coal power plant, to build a new coal power plant, very expensive. But build a solar plant, you can do it maybe fraction of the cost because you need only a lot of solar panels and inverters. Very easy to install. In a couple of years, you can build a solar farm. But you need about 7, 8, or 10 years to build a coal power plant. It's same with hydropower plants. You need about 7, 8 years to build a hydropower station. But wind turbines installation or coal solar plant installation is very easy and also cheaper. So that's the kind of trend. So we can't stop it. So there will be more and more solar farms, wind farms in the network. So we have to do work to ensure that we address the intermittency of these solar and wind farms, of inertial issues, inertia issues, frequency control issues, and also the system strength issues. So this energy transmission, it's real, it's happening, but so there are lots of challenges, but we can make it work. So as power system engineers, we have a huge role to play, I think, in the next decade, everywhere across the world, to ensure that we have means, we are prepared to ensure system stability and also supply reliability. Because normally those who are building solar farms or wind farms, they don't understand the power system operation. They just want to invest and get the income. Governments the same. Normally they don't realize the complexity of power system operation. So we have a huge role to play as power system engineers to ensure that we transition, we go from the present system to this renewable rich system in next 5 to 10 years in a stable and safe manner. Yeah, that's my presentation. Yeah, thank you for the time. If you have any questions,